everyone. Welcome to the last day of this workshop. So the first speaker this morning is Thorsten Heidersdorf, and he will tell us some recent results on representation theory of algebraic supergroups.
Yeah, so thanks a lot for the invitation. So I decided not to present maybe one technical theorem. I would rather like to give some kind of survey talk about some of the things that happened in the representation theory of supergroups. This will be a very biased survey, so I'll try to squeeze my name in quite often, and I will ignore many other results which were relevant. So my excuses to people that are maybe swept under the rug right now. So this is the setup. So I take a Lie superalgebra over the complex numbers. I will only look at finite dimensional Lie superalgebras, and so here are some examples. They are in fact all simple. So there is SLMN. If M is equal to N, that's not simple, but you can take a quotient PSLNN. Then there is the orthosymplectic Lie superalgebra. And then there are two strange ones. That's actually their proper name. They're called strange PN, periplectic, and QN, the queer Lie superalgebra. Then there are some exceptional Lie superalgebras, and then there are Lie superalgebras of Cartan type. And so the classification of Katz in the 70s said that these are all simple finite dimensional Lie superalgebras over the complex numbers. And for the sake of this talk, I will mostly, most of it will be here about this type A case, and I will actually mostly talk about GLMN. But if you understand GLMN, you understand the others. I will completely basically ignore the last two here, the exceptional ones and the ones of Cartan type. And the reason that I ignore the exceptional ones is the following. So this representation theory of, so the biggest difference of representations of Lie superalgebras versus representation theory of semi-simple Lie algebras is that the representation categories are basically never semi-simple. There's only one case here, the OSP 1-2n case, which has semi-simple representation category, but you can somehow measure the failure of semi-simplicity of these categories by something called the defect or atypicality. The exceptional Lie superalgebras have defect 1, so they're pretty close to semi-simple, and you can work out most questions in a brute force ad hoc way. And so from a representation theory point of view, they're not so interesting. Most of the questions that I will talk about today were settled longer ago. And I will ignore the ones of Cartan type because I just don't know anything about them, and they have rather weird representation theory. Okay, so I'm going to look at finite dimensional representations of these on supervector spaces. So if I have a supervector space, there's a Lie superalgebra GLV, where the supercommutator just gives you this bracket that you need for the Lie algebra structure. And in fact, I inserted a warning here. I will actually work with some full subcategory, namely I will only consider representations which integrate to the algebraic supergroup, so integrable representations. So that's a setup, and so basically the question is, what do we know about these finite dimensional representations? And so there's a lot of early work by Katz in the 70s. So for instance, he classified finite dimensional irreducible representations in terms of highest weights, pretty much similar to the classical theory. There are some difficulties there, that Borels are not conjugate and so on, so which means that you have to sort of fix a Borel and then you can determine which weights lead to, what is the condition for a weight to be dominant integral, and all this gets a bit messy, but I will ignore this. But yeah, so there is such a classification of finite dimensional irreducible representations, and he also, so once you have a finite dimensional irreducible representation, you can talk about its character, which is defined as in the classical case. So these have weight-space decompositions. So you can take the formal sum, dim, say L lambda mu, so the mu weight space of L lambda, and then e to the mu, and you can ask, is there a closed formula, a nice formula like the Weil character formula? And so Katz was able to obtain some character formulas, but it depended on the weight lambda. So what we'll see is that somehow that this failure of semi-simplicity makes the character problem to a very challenging problem because you don't have somehow a direct construction of the irreducibles. And so Katz solved this for so-called typical weights. And so yeah, here's that one statement that I mentioned before. So rep G is semi-simple. Well, okay, I made a mistake here because I talk only about algebraic representations, so let me correct this. That's very convenient that I have this G reductive. Or G is OSP 1 to n. And so that renders many tools from classical Lie theory useless. And so the questions that I want to consider today are the following. So first of all, you can look at rep G just as an abelian category. So you can ask, okay, what are the indecomposable objects? How many are there? Can I construct all of them? If this category is not semi-simple, this is caused by irreducible representations having extensions. So what are the possible extensions? These kinds of things, or what are endomorphism algebras of maybe projective covers, all kinds of things. The second question is very simple. What is the dimension of an irreducible module? So for the classical case, there's a Weil dimension formula, which you readily get from the character formula just by taking some limit. But we just saw that the character problem isn't so easy, so it's not completely clear that you can do this. Then you can ask for the superdimension. So these are representations are super vector spaces with a G action. So for super vector space, you can take the superdimension, dimension of the even part, minus dimension of the odd part. And then you can ask, what is the character? Is there a nice formula? Then you can ask, well, what are the fusion rules? So if I take two irreducible representations, I can tensor them together, and I can try to decompose it. And the lack of semi-simplicity will mean that, unlike in the classical case where this is always completely reducible, this will only decompose into some indecomposable representations. And you can ask, okay, which indecomposable representations come up, with what multiplicity, and so on. And the last question that you might ask, what are branching laws? When you embed some subgroup and you restrict, and how does it split? And in fact, the branching laws, the fifth problem is actually a special case of the sixth. And so what is the status? I basically gave you the answers here, and I will try to basically explain the answers that I gave here. I think I forgot, well, so the answer to one is mostly okay. So mostly okay means the following. First of all, in general, you cannot classify the indecomposables of these categories. There are just too many. Technical term is wild representation type. But people worked out precisely when this happens, when you have when you can classify the indecomposables and when you cannot. If you go back to the list here, so if you take SLMN and either M or N is 1, then you have so-called tame representation type, and there is a classification of the indecomposables. But as soon as M and N are both bigger than 2, you cannot classify the indecomposables anymore. Similar things happen for OSP, Pn, and Qn. The exception always have tame representation type, and people have worked out a complete list of indecomposable representations. And if you look at, so what do I mean then with mostly okay for OSP and GLN and so on? Well, so for GLMN and OSPM to N, I think you have as much control as you can possibly hope about these questions like X1 or how do I construct indecomposables. So there's, for instance, there's a complete description when irreducibles have extensions and so on and so on. I'll talk about this a bit later. There's mostly work due to Brandon Stroppel and Erik and Stroppel. So then the dimension of the irreducibles. So yeah, for most cases we have dimension formulas, but they are mostly pretty bad. So they are after all explicit, so you can put it on a computer and the computer will do it for you, but you don't want to work with them often. Theoretically, they're ugly and certainly not optimal. So that's true for GLMN, OSPM to N, Qn. I think for Pn it's open, that's the only open case. The superdimension problem is much easier. Some of the superdimension seems to be the right analog of the dimension here in the superworld. So in that case, I think we have a complete solution. I'll talk about this a bit later. Character formulas, well, character formulas are mostly known. The one exception is again Pn, in which case we have some kind of infinite character formula. For the others, we have finite character formulas, but they are again often not very pretty, but it's getting better and better. And of course, somehow the answer 2 basically comes from answering question 4, because you can take again some limit, evaluate this character and get the dimension formulas. But the problem is that these characters have sort of alternating signs, which doesn't matter too much for the character formula, but then when you sort of evaluate this limit, you get some dimension formulas which have lots of alternating terms, and that is something you don't want in a dimension formula.
Is it the superdimension signs?
Mm-hmm.
Is the signs corresponding to the superdimension instead of the dimension?
Well, I mean, no. The signs come from, so one easy case how signs can arise is that no, essentially they have nothing to do with the superdimensions, the signs that come up. Because if you take a, let's say, character formula, you really just take the formal sum over the dimensions of the weight spaces. So you're not looking at superdimensions of weight spaces. You can also take the super character, in which case you, but that's not the one you would try, that's not the one you would use to get dimension formulas. You would take the super character to get the superdimensions. Yeah. And in fact, in that case, you have nice cancellations, and you could use the super character formulas to get superdimensions. That's one way to get it. But the signs in the character formula have sort of different origin.
Right. Okay. The super character is probably nicer in some sense?
Yes, it's often nicer. But okay, well, okay, I want to withdraw the answer. It depends on the group that you consider. So for GLMN and OSP, M2N, the super character and the character are actually almost the same. So it turns out that for those Lie superalgebras, the dimension of, so weight spaces are either purely even or purely odd. So it means whether you take the dimension of a weight space or the superdimension of a weight space doesn't really matter. They're the same up to a minus sign, plus minus sign. So that means when you take the character or super character formula, they're basically the same up to sign factors that appear there. So if you know one, you know the other. And that's, for instance, not true for Qn. For Qn, weight spaces always have the same even and odd dimension, so the superdimension of every weight space vanishes. So it means that actually for Qn, the super character completely identically vanishes for every irreducible representation.
So except there's no consistent grading in the white space.
Yeah, I mean, yes, exactly, yeah. Yeah, so weight space are yeah, so the dimension of the even part is exactly the dimension of the odd part. And so that means that for Qn, the super character vanishes, but the character is highly non-trivial. Okay, so yeah, then fusion rules. Yeah, that's really a difficult case. And here we only know special cases. I will talk mostly about GLMN, where we have partial results. And there are partial results for OSP, but beyond that, I think this is unexplored and very difficult. And then I won't even talk about branching laws. I think that unless you take extremely special representations, like, I don't know, standard representation or so, we don't know what happens when you restrict to certain subgroups. I mean, so sometimes low-rank cases were worked out, like SL21, and you bet in SL11 into SL21. These kinds of things might be known, but there are no general formulas at all. Okay, so let's focus maybe in the beginning on GLMN. So here's just a brief reminder. I mean, I think GLMN, SLMN came up frequently, so maybe this is a bit. So I will be very brief. So these are all endomorphisms of this super vector space CMN, where I just view this here as even and this here as odd. And then if you choose a basis in the usual way, and then you can identify these endomorphisms of matrices. There they are. These are block matrices. And the bracket is given by the supercommutator. So here you have these, so x, the symbols mean the following. You take a homogeneous x and a homogeneous y. So homogeneous means either purely even or purely odd. And if it's purely even, you say the parity is 0, and if it's odd, you say the parity is 1, and that defines this x and this parity is here, and then you extend linearly. So that's the supercommutator that turns it into a Lie superalgebra. And maybe the first thing you want to do when you try to understand representations, you want to use the even subalgebra, which is given here by these block matrices AD, and it's just GLM cross GLN. And then you can start with an irreducible representation of this even subalgebra, and you can induce it. So first you extend to this parabolic, to this ABD matrices, and then you induct. And you get something finite dimensional in this way. This is called K lambda in honor of Katz. So it's called the Katz module. And this has a simple top. So it has a unique maximal submodule. When you mod out the submodule, you keep an irreducible module. That's a simple module of weight lambda. So the lambda here, when I started, was weight for GLM cross GLN. And so for each dominant integral weight of GLM cross GLN, I end up with a simple representation L lambda of GLMN. So in that way, I've produced lots of irreducible representations. And now this module might be simple or might not be simple, and you can very nicely characterize when this happens in terms of the weight, so there are conditions on the coefficients. And if it's simple, then you call this weight typical. And the name is well chosen because most weights are typical. If you would draw the weight lattice, somehow the ones that are not typical are somehow a thin subset. And so the slogan is that these typical weights are the good weights. They don't cause problems. And the whole failure of semi-simplicity is due to these atypical weights. So if every weight was typical, then the category would be semi-simple.
So if you take the kind of representations we're used to in physics, tensorial representations of fundamental or vector-like.
Yeah, they're typical. Well, no, they're not always typical. Well, okay, so if you take polynomial representations of GLMN, they're not always typical, but still V tensor R, so V is the standard representation, is completely reducible.
Maybe from the off as a physicist, I mean, this would be in physics notion sort of short multiplets. Yes. So if you have extra shortening conditions, that's what you get, what you call atypical in mathematics.
So what is the question?
Are these tensor, I mean, graded symmetric tensors, are they typical or atypical?
So you mean like something like sum of something of a standard or exterior powers of standard representations? No, they're not necessarily typical. No. Actually, I'll say a little bit about this. Yeah. Okay, and so and otherwise you call them atypical. And so I think I didn't write it. No, I didn't write it on the slides, but for instance, if you take now GLMN, you can prove that L lambda is projective, so it doesn't admit any extensions if and only if it's typical. So in that sense, really, the atypical weights are responsible for the failure of semi-simplicity. Okay, let's continue with GLMN, and so I'm going to introduce some graphical calculus, which is due to Brandon and Stroppel. I think it has become clear in the last 10 years that in order to understand these L lambdas and their properties, you should forget about the sort of the usual way to write dominant integral weights. So here, what you see on the right-hand side up here, these are basically dominant integral weights for GLM cross GLN. And these are just integer entries, and they are arranged by size for these two parts. So it's somehow the GLM part and this is the GLN part. And this gives you all irreducible representations up to parity shift. So when you have a representation, you can always replace it by its parity shift, where you just flip the even and the odd part of the supervector space. And they're not isomorphic if you only allow even morphisms. So you basically get two irreducible representations in this way. And so what I would like to do is I would try to forget this way of writing dominant integral weights. I want to attach to it something like a weight diagram and work with this weight diagram. And so here's how it works. You define two finite subsets, one of cardinality M, the other of cardinality N. And you see you just take basically the coefficients and you shift it a little bit. And the shift is sort of irrelevant. It's only you want to now label the number line Z with certain symbols. And you might, of course, have lambda 1 here equal to lambda 2 or something like this. And I don't want two symbols on the same position in the number line. That's why I introduce these shifts. Okay, and now I label my number line. So if I have something intersection, I label it by this down. Then there are finitely many remaining in this IX and I naught. So I label them by a cross or by a naught. And all others, all infinitely many others, I label by an up.
Sorry, a stupid question again. These lambdas are not Lincoln labels. They are lengths of things in some Young tableau. What are they?
Yeah, so I mean, what I take is, so I mean, if I take such a matrix, I have the obvious diagonal matrices inside. And then I take some of the standard basis of these diagonal matrices. I just take epsilon I and I evaluate on the j's. I just take so epsilon I takes the i's term of the diagonal entry, and that's what it gives.
Nothing like fundamental weights or...
No, these are not fundamental weights. No. And then, so I write my, so I write my lambda in terms of these basis vectors. Lambda I, epsilon I, and this is maybe from 1 to m. And then I have okay, this was. And yeah, these epsilons are the obvious basis functions on the diagonal matrices, which give me my Cartan subalgebra. And that's what you see.
Sorry, I have a question. Okay, when you actually you talk about the supervector space, then you say that you can shift. I mean, you can change the parity. So you
yes.
Can, okay, but can you remind me what happened if there is this metaplectic representation? Were there are such representation in this case? So if you shift from, I mean, if you change the supervector space, the parity of the supervector space, don't create this metaplectic representation? Or I'm wrong? Probably I'm wrong.
These representations are finite dimensional, and the metaplectic group doesn't have interesting finite dimension.
Oh, that's right. All infinite dimensional representation. Okay.
Except the
okay.
dimension.
Okay. Thank you.
Okay, so here I just drew a picture of how this might look. It's a weight diagram. Of course, it goes infinitely to the left and the right. And so here you see finitely many of these downs. There are a finite number of these crosses and knots, and all the others are these ups. That's how this weight diagram looks, and the weight diagram uniquely determines the weight. You can retranslate. Okay, and now when I take this weight diagram, I want to attach caps. So I go from the right to the left through this weight diagram. So let's do it here. And so what I do is I always connect downs with ups, and I connect a down with the next up, next free available up to the right. So if I'm here, oops, I join. Oops, so this was wrong. I join these here. Then this was wrong. Then I join these here. I join this here. This here. Now here I have to jump here. And so on. And okay, here I have to draw this huge cap. Okay. And somehow this seems to be the right way to express many properties of these weights. So I'll talk about some later on, but For instance, you can very nicely express the superdimension of L lambda in terms of some of the structure of these cap diagrams. I'll make a precise statement later. But for instance, you can also study the effect of translation functors on simples. So translation functors means the following. You have the standard representation or its dual. You tensor your irreducible representation with the standard representation, and you project somehow to some, say, eigenspace of a Casimir or whatever. And you want to know what happens to this irreducible representation, how does it transform. And you can very nicely express this typically in such a diagram, because essentially it means like moving, you take some position here in your diagram, and it just means you flip the two, something like this. And so this is a very convenient way to express such translation functors. If you want to know, for instance, what are the possible x1 between two irreducible modules, so first of all, if the two irreducible modules don't have the same positions of the crosses and the knots, they are never extensions. So in mathematical terms, these crosses and the knots, they determine the block of the irreducible representation. And so let's take two representations with the same labeling of crosses and knots, and then you can transform your irreducible representation the following way. You can take such a cap, and then you see it always has this down on one side and an up on the other side. And now you can flip the two. It means that you just shift this here, and you shift this here. And it gives you a new weight, a weight diagram of a new weight. And the statement is you have a non-trivial x1 between two irreducibles, either if and only if one is obtained from the other by such a switch in one of the caps. You are only allowed to switch one cap. You know? And so, and you look at this weight diagram or this cap diagram. For instance, here, if you express this again in terms of these lambda i's, you don't see anything. You don't see any rule because you have these huge switches. And so this seems to be, such a structure seems to be invisible if you just write this as a sum of these lambda i's. Okay, so let me just mention, and I will be extremely brief, that there's some theory behind it, and I don't think it's really suited right now, but so what is behind it is a theory of Brunner and Stropel of so-called Kovanov algebras. So what I mean is the following. So you can split your category rep GLMN into so-called blocks. You look at, you check when two irreducible modules can have sort of iterated extensions. This defines an equivalence relation on the set of irreducible representations, and you look at all the intercomposite modules that you can form with an equivalence class of irreducible representations. That gives you this block decomposition. And then you take, you define the so-called locally finite endomorphism algebra, which are called N, fin, P, gamma, where you just sum up of all these HOMs between these P lambda i's and P mu j's. So these are projective covers. So remember, the category is not semi-simple, but it has enough projectives. That's what Vera gave an argument yesterday for this. So that's the projective cover, and you can look at the homomorphisms between this, and you sum up over this. And then you can look, this is an algebra, and you can look at modules over this algebra. And this equivalent is an abelian category to this block that you started with. This is just abstract nonsense. You can always do this in case you have something like a projective generator or something like an analog like this. So it seems it gives you a new way to think about this gamma or these subcategories, but in general, this is in this way it's completely useless because I mean describing this modules over this locally finite endomorphism algebra is as difficult as describing gamma. You just shifted the viewpoint, but you didn't gain anything. But the punchline is, and this goes back to Brunner and Stropel, that in fact in this case you can describe this algebra completely explicitly. It's a certain diagrammatic algebra, which they call a Kovanov algebra of type A. It's a diagrammatic algebra. Maybe you've seen something like a Temperley-Lieb algebra or a Bauer algebra. So these are algebras which are defined by some kind of planar calculus. And this is one of them, just much more complicated. And you can completely explicitly describe this algebra and its modules. And this language of weight diagrams comes from this planar or diagrammatic calculus. So there's a big theory behind it, but for my talk, I'll just use this ad hoc. I just use it as a very convenient way to express things about these L lambda. Yeah, so the slogan is somehow that the complexity of these cap diagrams measures how complicated L lambda is. So here's, for instance, one property. If you don't have any downs, then the weight is typical. Weight is typical if and only if there are no downs. And this is the case if and only if L lambda is projective. If you have one down, then it's called one atypical. If you have two downs, it's called two atypical, and so on. You can have at most minimum of M and N downs. So, and somehow this atypicality is a measure for the difficulty of this weight L lambda, how far it is off from being semi-simple. And so, for instance, if you, so I said you can have at most as many downs as the minimum of M and N. So, for instance, if you take GLM1, and for some reason I switched to the group, but I hope that doesn't cause confusions. So, for instance, if you're in GLM1, you can have either no downs or one down. So, you can have either typical weights or one atypical weights. So, here are weights which are very, very good, very convenient. So here's another example of a weight, a cap diagram. It takes these weights, which are k, 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 minus k, and so on. So this is called the case tensor power of the Berezinian. It's some kind of analog of a determinant power in the setting. And here you see the associated cap diagram. So this has high atypicality, maximal atypicality, in fact. But it's still an easy weight because somehow its cap diagram has this easy symmetric structure. So well, this is a very special case because you don't even have crosses or knots. But in general, because of the importance in the theory, if you have weights which have these completely nested cap diagrams, they get a special name. They're called constant weights. And so they're also good in the sense that while they may be highly atypical, we basically understand them very well. And so sometimes many proofs will use some kind of reduction to these weights. So as I said, they're called constant weights. So for instance, a typical or one atypical weight is automatically a constant weight. And so one way in which they naturally occur is if you take the standard representation, or the natural representation, and you take its tensor powers, and then you decompose it. And there's a little miracle here. This is completely reducible. So there's very, very few things that are completely reducible in this world, but tensor powers of the natural representations are among them. And so a long time ago, by results by Beryl and Regev and Sergeyev, these irreducible representations were determined that come up in this way, and they're all constant weights. But not every constant weight comes up as some irreducible summand. And you can strengthen this result, so you can look at mixed tensor powers. So the natural representation is not self-dual, and so you can look at this mixed tensor space. You take an R tensor power of the natural representation and an S tensor power of its dual. This is not semi-simple, it's not completely reducible, but in fact the indecomposable representations that come up, they can be classified, and we basically know everything about them. So we know the dimension, the very nice dimension formulas, we know their characters, we know even the tensor product decomposition between those is known. You can explicitly write down the composition factors or whatever you like about these indecomposable modules. But the drawback is all irreducible representations arising in this way, some summoned in some mixed tensor space, they're always constant weights. So you only get these sort of easy cap diagrams. And so if you can ask, okay, I mean, how restrictive is this? And it's extremely restrictive. So if you take a weight, say of atypicality k, how do you define this basically? Well, it means you distribute k down somewhere on the number line, anywhere you like. So it means that sort of this constant weights basically are very special because it would mean you'd sort of put all the downs basically next to each other to get something like this. And you see the difference to the classical theory. Because if you would take this mixed tensor space for GLN, you would get every irreducible representation in this way. But here you basically only get these constant weights. I should say there's something missing here. In fact, you can prove basically every constant weight occurs in this way. If you take mixed tensor powers up to some shift of this Bayesian representation that I wrote down. Okay, so that's GLMN. I think the slogan for GLMN, if I summarize, is that we understand the mixed tensor powers right now, but nothing else. You can move to the OSP case, and here I wrote actually the group on purpose because, well, there's the Lie superalgebra OSP, and the representation theory of this Lie superalgebra is the same as the representation theory of the algebraic supergroup SOSP, so the connected component of this OSP. But for it is quite, it's a lot more convenient to work with the group OSP than with SOSP, because this is, well, you have to otherwise worry about restricting to the connected component, and then things can decompose and things like this. Okay, so let me just be brief and say there is an explicit description of this endomorphism algebra of some kind of projective generator. This is due to Erich Stroppel, so you have the same diagrammatic calculus, just a bit more complicated. You can again define weight and cap diagrams. So people came up with slightly different notation, but otherwise this is morally the same. There are some differences. So sometimes in order to distinguish two weights, you have to add a sign to the weight diagram. And these weight diagrams have a minimal element always. So a minimal, so we are only looking here at n, the positive integers. That comes from the condition that the weights are dominant integral for OSP, so it means these are minimal elements. So you cannot take the lambda i's to be negative as for GLMN. So there is, it's a cutoff here. And so if you're at the 0 position, you allow, and you have atypical symbols at the 0 position, you can stack them. You can also introduce some variants where you transport them somewhere here, but yeah. But otherwise, you have a weight diagram calculus, you have a cap diagram calculus. All things are pretty much similar. So here's a cap diagram, and there's one special rule that if you have one of these stacked symbols at the origin, then sort of your cap has two arcs. You connect it to the next, so you connect it here and here. It counts as one cap, but it has sort of two ends. But otherwise, these cap diagrams serve the same purpose as for GLMN. So again, you can express X1s, translation functors, or whatever you like in terms of these diagrams. And let me just mention on the side that you can also introduce some diagrammatic calculus for Pn and Qn, but there's no analog, so this is sort of ad hoc. It's just a way of thinking about this it's just a combinatorial tool. There's right now no analog of this Kovanov algebras that control everything. I mean, people are trying to get there, but it's kind of complicated. So the analog of the mixed tensor space here is just, you take the natural representation, so V is just C to the M to N, and take its tensor powers. So there's no sense talking about mixed tensor powers because V is self-dual. This is not completely reducible, but as for GLMN, you can classify the indecomposable summons and you can determine the fusion rules. So very recently, even unpublished, you can also describe these indecomposable summons that occur in this way explicitly and do whatever you like with them. Like for GLMN, this was recent work by Nehme. It was a master's thesis that was just handed in September. But what you see, even in this case, if you look at the irreducible summons that come up in such a tensor power, they're again constant weights, where constant could be defined as for GLMN. This just means completely nested cup diagram. So again, very, very special. And so we again in the stupid situation that we don't, we understand these constant modules, but nothing else. Okay, so I want to say a few words about character formulas. I just noticed that I blathered a bit too much, so I have to speed up a bit. So as I said, for typical weights, cuts prove the character formula. That's the one here. This R is the so-called Weil denominator. It's independent of lambda. This is the so-called Weil vector here. And then, so the essential part is this one here. And it looks pretty much like a Weil character formula in the classical case. And then GLN1 was treated by Bernstein, Leites, and van der Joy, Kings. I forgot the list of people, but there were a couple of people, mostly from math physics, that proved this character formula here. But then, so this is sort of the one atypical case. Note, these are called constant modules, so this is also covered by the general theory nowadays. But beyond that, little was known for a long time. Then in the mid-90s, Saganova wrote down some kind of infinite character formula in terms of these Katz modules. So for these Katz modules that I find in the beginning, you can write down the character explicitly, and so you can show that every irreducible module has a resolution in terms of Katz modules, and you can count sort of the occurrences of these Katz modules and somehow invert, and this gives you some kind of character formula. And then over the years, people came up with finite character formulas, for instance, for GLMN, QN by Zhu and Zhang, but they're very, okay, this is on YouTube, I shouldn't say it like this, but they're very complicated formulas you don't want to work with. And then the only remaining case which is open, I think, is PN. For PN, you have a similar solution as Saganova's solution as for GLMN. So it means that there are, you can write down an infinite resolution by Katz modules, and you can determine the occurrences of these Katz modules. It gives you an infinite character formula. But as of now, there is no finite character formula for PN. And so here is the result I proved. It's actually from this year with Maria Gorelik. But this is for GLMN, and the OSP case had been treated previously by Gruson and Saganova. So there is a character formula which looks like this. It's a finite sum, and you sum up, so there's this BLL prime, so L prime runs over irreducible, in principle over all irreducible modules, but there's a finiteness condition built in, so it's a finite sum. And then KW for Katz-Wakimoto, because they considered those previously. So this has the following property. First of all, if you sort of get rid of this Weil denominator and this e to the rho, then this is actually a basis of your charactering. Secondly, if you take these coefficients into a matrix, there's a lower triangular matrix with integral entries, one's on the diagonal, and you can just turn it into a matrix with positive entries by multiplying the diagonal matrix with some signs on the diagonal. And so once you do this, so once you sort of adjust signs, these here, these BLL prime, they can be completely explicitly expressed in terms of this cap diagram combinatoric. So basically you have to see, you write down the cap diagram of L, the one of L prime, and you somehow can by some moves, you can move one to the other. And you count the number of ways you can do this. And what is a move, for instance? A move is what I told you, when you have a cap and you have a down on one side and an up on the other side, you can flip the two. And so you can move your weight. But this would be a move of weight 0. You can have sort of higher weight moves, where you have an external outer cup, which encloses some inner cups, and you can take some down and sort of move it in some way in the big arc. But whatever, I think the precise rule is not important. The important thing is there's a completely explicit rule. And so at the end, what you get is a finite sum with integral coefficients in terms of a basis of the charactering. So that's probably, well, it's subjective, but probably the nicest character formula for GLMN. And there's, so for instance, if you would take a constant weight, then in fact all these BLL prime would collapse. This would just be Kronecker deltas. So then the whole thing collapses. again, so some of the complexity of the cap diagram, how these caps are nested inside each other, expresses how complicated the weight is. And well, one application of these character formulas is that indeed you can get dimension formulas for this. You can also get complete formulas for the G0 decomposition of any irreducible module in this way, but the formulas are really not pretty. So G0 decomposition means the following. You can take your L lambda and you can restrict to the even subalgebra. And this gives you a formula for the decomposition, for the branching laws, basically in this case. But the formulas are really, really, really not pretty. And you can do this uniformly for GLMN and OSPM2N. Yeah, so these are character formulas, and that's how you get dimensions. So I said in the beginning that the superdimension problem is really solved. You could actually use these character formulas to compute superdimensions because, as I said, the superdimension is the super character is more or less the same as a character, and then you can try to evaluate the super character to get superdimensions. But I guess there's a better solution to the superdimension problem, which uses some kind of BRST operators. And I think these x here that come up were discussed in various talks. So you take an odd x, which is nilpotent, so xx is 0. Yeah, this kind of nilpotent varieties. So here's one example. You take zeros everywhere and just a little 1. Or you could take several ones here on the anti-diagonal, would also work. Or you could, of course, take ones on the diagonal, would also work. Something like this. And so if you apply this, if you act with such an element on a representation twice, you get 0. That's this condition here. So you get 0, and so you can talk about the cohomology. You just take the kernel of x, modulo the image, and I call this dsx. So V here is some representation in rep G. And I call it ds because of Duflo-Serganova, who defined this first. Studied this maybe 15 years ago. If you apply this to the joint representation, so to G acting on itself, you see that Gx actually has a structure of a least superalgebra. And so in this way, Duflo and Serganova obtained a functor which goes from rep G to rep Gx. And it turns out, and this is quite surprising, that this is a symmetric monoidal functor, so it's compatible with the tensor structures on both. And you can determine this Gx explicitly. So it's, for instance, if you take GLMN, you get GLM minus Kn minus K for some K. And here, if you would take these elements up here, it would be the K would be the number of ones on the anti-diagonal or the diagonal. So if you take a single 1, you go to GLM minus 1, N minus 1. You go down in steps of 1. And if you take OSP, you have this OSP N minus 2K, 2N minus 2K. And again, you can, depending on which X you take, you go down in bigger or smaller steps. And so this is a very powerful tool to reduce questions to lower rank. I mean, classically, you would like maybe to use restriction functors or something like this, but we don't know anything about these. So these Duflo-Serganova functors sort of allow to reduce many problems somewhat to lower rank and try to understand problems inductively. And so if you, now, let's iterate this construction. So we go down in steps of 1. At some point, so I will assume here for simplicity that M is at least as big as N. So if you do it then N times, you end up in GL M minus N, N minus N. So you end up in something well known and classical. And so ultimately, you end up in rep GL M minus N. And so you want to know what happens to your representation that you start with. Can I determine it? Because, I mean, this is a symmetric monoidal functor, it preserves superdimensions. So it means that if you can calculate what happens to a representation all the way down, you have a superdimension formula. Okay? If you can determine which irreducible or which isotypic or whatever representation of GLM minus N you get, you have a superdimension formula because the dimension You can just compute the dimension with the Weil dimension formula, and that's it. That's a superdimension. And so for that, you need to know what does this ds functor do on irreducibles. And so a couple of years ago, Weiser and myself proved a formula for dsx of L lambda. So here, the x is actually of rank 1 in the statement. So, and this is actually surprisingly semi-simple. So irreducible representation goes to a semi-simple representation. And these L lambda i's that come up in this formulas, they're obtained by removing a maximal arc from the diagram. So an arc is, or a cap is maximal if it's not enclosed by any other cap. So for instance, if you take a cap diagram like this, you see there are sort of 3 maximal caps. It gives you 3 summons. Now, these summons might come up with a parity shift. So the pi is this parity shift, and it sort of measures if lambda or lambda I have the same parity or not, modulo 2. So there's a completely explicit formula. And in particular, this ds of L lambda is semi-simple and multiplicity free. And well, so when you go down all the way to GLM minus n, you actually, if you start with an irreducible representation, you get an isotypic representation. You just have to count the number of times this irreducible representation appears. This is this number m lambda here. And well, we showed that, I mean, this was previously known due to Weiser, but we showed that this m lambda has a very explicit expression in terms of this cap diagram. You basically, what you do is you read a cap diagram. You view it as a tree by starting from the outermost cap and going inside. So here I have done the translation. So this here corresponds to this tree, and this here corresponds to this tree. And so the nesting structure of these caps gives you the tree. So the union of trees, in other words, it's a forest of planar rooted trees that you get. And then you can express this lambda, this number m lambda in the following way. You take the number of nodes of this forest, and you just take the factorial, and you divide by the so-called forest factorial, where you sort of, which is recursively defined by going through this tree, and then, for instance, here, and then counting how many nodes are there, and then multiplying all these numbers together. So that's this m lambda, the multiplicity of this isotypic representation is a number between 1 and n factorial. And then this gets multiplied with the dimension of this irreducible representation of GLM minus n, to which this L lambda is mapped. And so, for instance, if you have a constant weight, well, m lambda is 1 if and only if it's a constant weight. Okay, so this is the superdimension formula, and now I want to basically skip this part here because I have something else that I want to treat. Let me just say that the whole theory can be done for OSP in a similar way, so the ds functor is there. It just, so again, ds of L lambda is semi-simple. Again, there's a completely explicit rule how to remove that the summons corresponds to sort of maximal caps. Big difference is that there is a multiplicity edge which can be 1 or 2. So sometimes a summon comes up twice. It's no longer multiplicity free. And the rule, when this mi is 1 or 2 is quite involved, so I won't tell you. You have to, for instance, if you take some cap, you have to count sort of the number of empty positions between that and sort of the minimal position, and depending on whether it's even or odd, and whether you are in the OSP 2m plus 1 or OSP 2m case, you get either 1 or 2. But again, a completely explicit rule, and of course you can play the same game as for GLMN, you can go down all the way. So if you do this for if you do it for OSPM to n, you end up either in representations of the orthogonal group, or the symplectic group, or the orthosymplectic group 1 to n, which is semi-simple and for which we know the dimensions. And so again, you get the superdimension formulas in this way. let me just, as a warning, say for Pn, this ds over lambda is not always semi-simple, but you can still sort of, if you go down all the way, and for Pn you would end up just in supervector spaces, then of course you get something semi-simple, and you can count the number of composition factors, and you still get a superdimensional formula in the same way, so it can be again expressed in some kind of forest combinatorics, like for GLMN, like for OSPM2N. And for Qn, the problem is uninteresting because, as I said before, the superdimension vanishes always. Okay, last topic, fusion rules. So a big unknown. As I said, for GLMN, if you have constant weights, which includes, for instance, GLM1 completely, you have a closed formula. Similarly for OSPM2N, as long as these are modules that come up in some tensor power of the natural representation. Then there are some low-rank cases that, I mean, for instance, physics literature, you find fusion rules for SL21 or so. There's, for instance, so SL21, for instance, was done by Götz-Queller-Schomerus, and there's some, the special case PSL22 was treated. But beyond that, I think we don't know anything. So there's this short sentence here, character formulas don't help. First of all, character formulas will never see the decomposition into indecomposable summands, but you could hope that at least it gives you the composition factors. It shows you what happens on the level of Grothendieck groups. And I just made the claim that we have these nice character formulas now in terms of these basis functions on my charactering. But it is a complete mystery how to multiply two of these Katswaki-Moto terms and expand it in terms of Katswaki-Moto terms. So I have no clue what happens there. So character formulas seem completely useless. But the last thing I want to mention, there are somehow truncated fusion rules. Something I did in the last years with Weissauer. So you can calculate the tensor product up to superdimension 0. What I mean is, if the superdimension of L lambda and L mu is 0, which happens pretty often, and then we don't know anything about these decompositions. But if you take L lambda and L mu, which has non-vanishing superdimension, then you can basically do the following. You can just kill all your indecomposable modules of superdimension 0 from your category. And there's some categorical way to do it. And you end up, what you get is astonishing, not some stupid category nobody can say anything about, but you get again the representation category of some supergroup or supergroup scheme. But this time, this is semi-simple. And there aren't many semi-simple supergroups, right? There are reductive ones and OSP 1 to n. So whatever this group is, this mysterious group G red, it must be somehow some limit of either reductive groups or OSP 1 to n. And so the basically vague version, or first approximation of a theorem I proved with Weissauer is if I don't take the full category rep GLMN, but I only look at modules that come up in iterated tensor products of irreducible representations. So I tensor two irreducible representations, I pick up the indecomposable summands, I tensor them, and so on. I iterate. That defines a monoidal subcategory of rep GLMN, and I kill these indecomposables, then this G red can essentially be determined in terms of classical groups. Classical groups means like SLNN, SP, SO, orthogonal group, and so on. And so what does it mean in down-to-earth terms? It means the following. You take an L lambda, an irreducible representation. So this defines an irreducible representation of this G red. Now, you do this for L lambda and L mu, and then you tensor these irreducible representations of G red together. Because it's semi-simple, it's going to decompose completely. And hopefully, you understand these fusion rules for G red, which will be the case for GLMN, because these are, after all, just classical groups. And then you can sort of lift this back to your original category, and you get a decomposition of L lambda tensor L mu. But because I've killed all the indecomposables of superdimension 0, this is a truncated fusion rule. I never see superdimension 0 summand. I only see non-zero superdimension. And these I nu here, of course, then might not be irreducible. There are some indecomposable summons which correspond uniquely to these L nus that come up in this decomposition. And so this is abstract nonsense. This is always true, whether you talk about GLMN or OSPM or PN or whatever. The big question is, can you determine these V lambda, V mu, G red explicitly? And if so, you basically get some truncated fusion rules. And so the answer is that yes, you can essentially almost completely determine G red for GLMN, and it's of the form GLM minus N times some group which I call HMN. This HMN is a subgroup of some infinite product of groups H lambda, and these H lambdas, these are classical groups, which we can basically determine, and we can exactly say, well, if you take L lambda, what irreducible representation of this big group it corresponds to. And so it means that when you take an L lambda, it has sort of a GLM minus N part, and it has this HMN part. So it corresponds to an external tensor product of a GLM minus N representation and an HMN representation. And so if you want to tensor these two together, it just means that the fusion rule will be a mixture of the fusion rule for GLM minus N, which is just the Littlewood-Richardson rule, and the fusion rule for this HMN up to superdimension 0. And so just to finish things off, here is an example. So I just listed a few groups for GL44. I use a shortcut notation here. I'm only looking here at weights which are highly symmetric. So where you see it's just mirrored with a minus sign. You might wonder why I'm looking at these special weights. Well, the answer is actually if you take GL44, a weight only has non-vanishing superdimension if it has this perfect symmetry here. And I just use this shortcut notation then. Lambda 1, lambda 2, lambda 3, lambda 4. And here I'm going to list a few small weights. And here you see the groups that appear. So these are these groups that are on the right-hand side of the theorem. Let me just go back. So there's always this GLM minus N factor. I'm ignoring it, okay? I'm just showing you these here. And you see these are classical groups for which we understand the fusion rules, of course. The C is for compact, so I'm stating the compact form here. And so there's a little very annoying drawback. So I said we can almost always determine the V lambdas and the H lambdas. For some weights we cannot. And so here this SO24 could also be some kind of semi-direct product of SL12 and something. So, but all the others are fine. And you see these explicit classical groups emerging, and so it means that the tensor product decomposition for GL44 is up to superdimension 0 actually completely classical in terms of classical groups. So this is something that could be done in principle for other groups, but it's very hard actually to do it. So this is only known for GLMN. And some, I think, recently Saganova announced that she can do some sort of defect 1 groups, so small rank groups, exceptional supergroups. Okay, I think I've already run over time, so yeah, that's it.
Thank you very much. So please, if there are any questions, so probably by shouting, from should work, but I can also pass on this.
So this technique where you deform the Lie algebra by a square zero element x, this looks very much like what we do when we twist a supersymmetric field theory. Is there some kind of interpretation what happens to the representations once you do this, which kind of connects to twisting or something like that?
Well, I'm not very familiar with this twisting technique, so I can't answer the question.
What was the last sentence? I didn't understand.
So I was wondering if there is an interpretation of this technique which connects to the procedure of twisting.
This is twisting. This is a kind of twisting.
Yeah, sure.
This is called twisting. Yes, you go down. You introduce this additional x, and then physicists say take BR as t cohomology, which is just what this ds exists. The observation, which is I think not made in physics by Duflo and Saganova, is that this procedure is a tensor functor, which is a very crucial observation. It's very simple to prove, but was not detected, and that's very important. So I think if you have something, you compute Feynman integrals, things like that. Yeah, you have tensors of certain fields whenever you make an explicit computation, and Feynman integral actually is a contraction. You have a huge tensor product over the space, so to speak. Yeah? The space is a space of all functions on it, and then some fields which are finite dimensional representations. You twist something infinite dimensional with finite dimensional fields which have values in the finite dimensional representation. If you do this, at the end, the Feynman integral is a contraction. It's a projection on one-dimensional representation. But the key observation, all these tensors appearing in the space of functions, the value fields and so on, you contract them by dualizing all this stuff. This is a tensor functor. This is very essential. So it factorizes, and if you produce these twistings, you can still keep information, and this information is very crucial. I think it's not so much observed or used in physics literature, and I think it's a very useful observation. It's very powerful in math, and should be the same thing should be relevant. For instance, when I became interested in this list was key for me. I should say this. You see SU2 and SU3, there's a U1 missing, which is coming from the Barracene. And what made me interested in this whole stuff is there a hidden way to explain the standard model? You see, you introduce Geo44 is the SU24. It's the conformal group for Minkowski space. And you see, if you have field theories on Minkowski space or boundaries of alias phi, which are compactifications of Minkowski space, which have values not in complex numbers, but in finite dimensional representations of the conformal. One of these especially. And you are dealing with these fields and compute Feynman integrals. What are you doing? You make contractions, and these contractions are tensor functors. So if you have certain energy ranges you are considering, well, these Feynman integrals have the property that terms where you evaluate that have superdimension 1 do not contribute. You know, this is a typical idea in physics. They have this point where everything comes together is a certain energy range, where you have cancellations. You have these miraculous cancellations between even and odd. And I think physicists often are interested in super representations of superdimension 0. Yeah. But you should be very careful. I think in certain energy ranges it might be so that all even and odds seem to asymptotically cancel. If there is a field theory with this property, what remains is superdimension different from 0. And then this is the maximal atypical representation. The most important representation there is the one-dimensional representation. Because if we integrate, compute a Feynman integral, you get a value, which means you project this huge tensor product on the one-dimensional representation, which is maximal atypical. So you see what remains could be the as a different, all computions from modules of superdimension theory could, at a very high energy level, could have vanishing properties asymptotically. And then what remains is you can approximate your complicated supercategory by this reductive, this quotient. And then the whole contractions here reduces to classical group reductions, exactly by these groups, SU2, SU1, SU3, SU5, SP6, SU12, SU8, SU12, and perhaps an SO24. Which means it could be that these are extended in a hidden way, in an approximation of a category of supergroups, that they're in a hidden way as a quotient category. These classical groups appear, the standard model appears as an approximation at a certain
low energy.
Certain energy.
Okay, thank you. Other questions? We can continue over coffee, actually, because we have coffee break, right? So we have time, maybe let's come back at 11:15, and let us thank Thorsten one more time for his talk.